Galvanic cell. We saw in grade 11 that a zinc rod placed in a beaker containing copper sulfate solution will slowly react with the solution. Copper metal is deposited on the zinc rod and is seen as a reddish-brown deposit, while the zinc metal goes into solution as ions. The blue color of the solution slowly disappears as more copper ions are converted to copper metal. Recall that this is a redox reaction. Zinc metal atoms get oxidized to Zn2+ ions and lose electrons. Cu2+ ions, in solution, gain electrons and are reduced to Cu metal. These reactions take place simultaneously. Note that the electron transfer is directly from the zinc metal to the copper ions, since they are in contact with each other. Heat is transferred to the surroundings in the process. If we are able to make the electron transfer happen indirectly, we may be able to create an external current. We need to separate the reduction and the oxidation parts of the redox reaction. We separate the zinc metal from the copper sulfate solution. The zinc rod is placed in a zinc sulfate solution in a beaker. We also take copper sulfate solution in another beaker and place a copper rod in it. The two rods are connected by a conducting wire to form an external circuit. We would expect the electrons lost by a zinc metal atom from the zinc rod to flow through the wire and reach the other end. Where a copper ion in solution accepts the same electrons and forms an atom of copper. This would be a spontaneous chemical reaction. However, this does not happen. No current flows through the wire, as shown by the ammeter. The reason is that we haven't completed the circuit. The flow of current requires electrons or other charge carriers, such as ions, to flow in a closed circuit. We add a salt bridge to complete the circuit. A salt bridge is a U-shaped tube containing an inert solution such as KCl or NH4NO3. The salt bridge between the two solutions in the beakers allows electrical contact. Cotton plugs prevent the mixing of solutions, but allow ions in the salt bridge to move freely into the two solutions. When the switch is closed, the circuit is complete. Electrons flow in the external circuit from the zinc anode to the copper cathode. Recall that oxidation occurs at the anode and reduction occurs at the cathode. The half reactions that take place at the anode and at the cathode are seen here. Zinc gets oxidized, goes into solution, losing electrons. These electrons travel through the external wire to the copper cathode, where a copper ion gets reduced, gaining these electrons and depositing on the copper rod. At the salt bridge in contact with the oxidation half cell, the anions, negatively charged ions, flow from the salt bridge to the electrolyte. At the salt bridge in contact with the reduction half cell, the cations, positively charged ions, flow from the salt bridge to the electrolyte. This prevents the buildup of cations around the anode and of anions around the cathode, maintaining electrical neutrality of the two electrolytes. We have created a galvanic cell, which converts chemical energy into electrical energy.
Starting to feel it? Now go master it with Maski.